Hi, everybody. We're here to do some more triple integrals. And in this time, we're going to be doing them in the cylindrical and then spherical coordinate systems. So, hyped. Um, Here we are with the cylindrical coordinate system. It's just like the polar coordinate system for when we were doing double integrals and polar coordinates. Notice that we have that same area differential for the bottom part of our volume differential. So we've got that r times dr d theta for the bottom part. And, now in order to make this a volume, kind of a chunk out of a cylinder, we add in the dz for the vertical component, and then we get, a volume, kind of like a cantaloupe or something like that. So overall, the volume differential will be r dz dr d theta. And similar to the polar coordinate system, it's gonna make sense for us to normally just do the integration in this order, with z being on the inside, the first one that we do, and then dr d theta. And that's just some stuff to remind you guys, this to some extent at least. So yeah, as we are setting up a triple integral in cylindrical coordinates, there are, three major things that we want to pay attention to. The last two are kind of exactly the same as the double integrals in polar coordinates. We would be looking for a function along an inner radius, and then a function along an outer radius in the xy plane. And then you have these rays for different theta values, A and B for where you start and stop. But then the new thing, cylindrical coordinates, is that we look for a z surface, of, some function of r and theta, normal functions like we're used to thinking about, being the top function and then one for the bottom function. And those are what goes on your bounds every time. So top surface on top, bottom surface down here, inner radius on the bottom, outer radius on the top, and then your two values for theta to bound it in the xy plane that way. Those are the three things that we're going to pay attention to as we set things up. And why don't we try our hand at doing that real quick here on example 1. Now, you notice I did not erase things, but I'm going to erase some of this. I'm highly tempted to not erase all of this, because I hate going through all these steps of actually solving the integrals. I always make mistakes. Anyways, I think it's important for us to look over this and try to set up this integral pretty well. Okay, what we have is a volume of a paraboloid solid bounded below by the paraboloid and above by the plane z equals 1. So real quick, as a visual here, we have our paraboloid in blue, plane on top, but remove it. So this whole thing is the volume that we're trying to capture. And in the cylindrical coordinate system, I've, highlighted some things to help us think through. So yeah, the cross sections that we would be looking at in this kind of an integral look like this. And adding up the cross sections, you would think about, we would be creating a whole bunch of cross sections from, in this case, it's the entire paraboloid, 0 to 2 pi will be boundaries on theta. But yeah, I guess I'm going out of order there because let's go back to the notes. In order to, do this, normally we think about the innermost integral first and then figure out the later ones later. So if we want to put some bounds on z, below we are bounded by the function z equals x squared plus y squared. And, we know that in polar coordinates, x squared plus y squared is r squared. So, yeah, this one means that z is equal to r. And so now we have the lower bound described as a function of r and theta, in this case, star. So r goes down there. Then above, by z equals 1, 1's going to go up here. Now we need to think about the boundaries on our radius, r. And normally we would find those by looking at the intersection of the lower and the higher surface, when we're defining the region this way. So, yeah, the intersection between the plane at the top and the paraboloid at the bottom is going to be this circle. And, if we're working with the equations, all we would have to do is set, make a substitution here and set these two equations, these two functions of r here equal to each other. Yeah. So that, we would set 1 equal to r, and that would be our outer radius, and we would be going from the origin along the z-axis for our inner radius. So, we're starting at r equals 0 and going out to r equals 1. I guess that's maybe not too exciting. Then the last one, since this region, r equals 1 is just a normal circle, the unit circle actually. In order to get all of that, we're going to need to go from 0 to 2 pi in, this last one. Okay, so 0 to 2 pi for, that outer bound on theta. Then you just go through the motions of inner integral first, then the middle one, and then the outer integral last. And eventually you get to pi over 2. And if you want to pause and look at any of those details, feel free to. But I think that's good for now. Example 2 is one of our, favorite kinds of applications. Here we are finding the mass and the center of mass of this paraboloid solid if it has a density function that is not completely trivial. This density function is 1 minus z. So if we want to go back to that picture that we had, if our density function is 1 minus z, it would mean that our density would be highest at the bottom and lowest at the top. So density would be lower up top because you'd be doing like 1 minus 1, which would be 0. And it would be more dense at the bottom. And so, we will find the mass and then the center of mass according to that density function. Very conveniently, this density function does not include x or y, meaning that we're not going to have lopsided mass in this object. the paraboloid is already symmetrical about the z-axis, and this density function doesn't change that. You know, if it was heavier on one side, you know, X or Y or whatever, then we would have to do more than what's here. You know, because the only moment that we're looking at is the one with respect to X and Y here, where we multiply by Z. And, you know, we don't have to solve for the moments in the other directions because this object is already symmetric around those other ones. So the other moments are always going to be 0 in the X direction and the Y direction. But, you know, to get the center of mass in the Z direction, what we do is we, take the moment in the Z direction and divide it by the mass. The mass integral just looks like what we just did for finding the volume, except instead of 1 minus Z is our density function. Still using the RdZ drd theta for our volume differential. And in that integral, you get pi/6. In the moment integral, where you multiply by Z in front of everything else that we had in the mass integral, you get pi/12, and then when you divide those two things, you get 1/2. So the interpretation of this one is, since we are heavier at the bottom and lighter on the top, the center of mass actually ends up being halfway through, even though there is a larger volume in the top half, since it's of a lighter density, you know, the center of mass still ends up being halfway through. So that's kind of cool. All right. Moving on. Example number 3. There's a lot there. Determining the mass of the solid bounded by this red cylinder and the XY plane and a cone above it, that's, you know, the blue part, given that its density function is equal to X. So this one will get denser as you go out in the X direction. I made a Geogebra thing to dramatically show that. So one of the things here, you know, when we're doing triple integrals and we want to visualize a density function, like we don't have a fourth dimension to dip into in order to describe the density function. Like we're already using 3 dimensions to show our volume. And so one of the ways that you could do that is actually color the volume that you have. So real quick, ooh, actually, yeah, ooh, look at that. If I color this via the rainbow, the red slice, you know, this portion would be of lower density. And as you progress along the rainbow, you would get higher density. So this is going to have a low density over here to the left, and then higher density as your X value increases. But I don't know, that kind of gives you an idea of, yeah, there's going to be some kind of gradient of density along this, and it's strictly in the X direction. All right. All right, back to the problem. Goodness. All right, how much of this should I erase? Okay, let's erase a decent chunk of this. We at least want to do a good job of setting everything up. Oh man. But you can come back to this if I mess this up. We might be looking at this again for reference. All right. So erasing everything and pretending that you don't see anything down here for now, because I don't want to erase this. I don't want to have to do those steps again. Oh, look at this. In this integral, you end up having to do a u substitution. Oh, big integrals. Great. Odd power and cosine. Okay. Back to setting this thing up and doing a good job. Right. We need to think about our z-bounds. We are bounded below by the xy plane, and we're bounded above by this cone. Okay. So below, let's use green. Below, we're going to be at a z value of 0, and above, we're going to be at this z value. This will just be z is the square root of r squared, or just r. So z is going to go from 0 to the cone, or r. And then to get an idea of, our boundary in the xy plane, and think about our inner radius and our outer radius, what we have here is a circle that's been shifted to the right, 1 in the x direction. So this is a unit circle, but it has points, or endpoints at the origin, and then over at x equals 2, because we've been shifted over 1. And so if we're thinking about an inner radius and outer radius, or inner radius and outer radius in this context, we're always going to be starting at 0. Let's do red for this one. We're always going to be starting here at the origin. And then our, outer radius is going to hit this function out here. And in order to do a good job of that, oh, great, this is the part that I erased. I think we need to put that into, polar coordinates. Let's do that. So, if we expanded this thing out, we'd have x minus 1 squared plus y squared equals 1. X squared minus 2x plus 1 plus y squared equals 1. Then we could change the x squared plus y squared into r squared, and we could change the minus 2x into minus 2r cosine theta. So the x squared y squared turns into r squared, and then minus 2 r cosine theta. We'd still have a plus 1, and then we would equal 1. So solving this for r means that we would want to go for subtracting 1 from both sides, and then taking an r out. And so this r on the outside, gives us our starting point. When r is equal to 0, we're on the edge of this thing. But the other one that we need to solve for is this, where r minus 2 cosine theta could be equal to 0. And if that's the case, then r would be equal to 2 cosine theta. And now we have r expressed as a function of theta, And that's the outer radius that we need to go to. So it was already written here. So hopefully we reach the same thing. Going back, label our middle integral now. We would be going from a radius of 0 to a radius of 2 cosine theta out to the edge of that circle. Finally, we need to figure out bounding rays for these parts of the circle. And honestly, if I just had to eye this up, I'm thinking that our bounding rays are going to be along the y-axis here because, yeah, I don't know. If you're going around the circle, yeah, you're going to have little angles off here. Anyways, yeah, if you're trying to make rays that go out and trace the whole circle, it seems like you're going to have to trace around this whole half plane. In order to do a good job of solving for theta, though, we set these equal to each other, 2 cosine theta equal to 0. I'm going to do this over to the right-hand side. So we're setting those bounds equal to each other to find where they intersect. And then this is just where the cosine is equal to 0. And that happens when theta is at, pi halves or negative pi halves. So the boundaries over here, kind of like, exactly what I had eyed up, are negative pi halves and pi halves. Okay, so that is the hardest part of this, translating everything into an integral that you could then solve. I guess one part that I did not do, that I just had, underlined here, and I didn't actually do a good job of showing where it came from, is this r cosine theta in our integral. That r cosine theta is the density function, and translating into polar coordinates, x turns into r cosine theta. And then the rest of that is just the volume differential. But then, yeah, you go through this, evaluate inner integrals, you eventually get to this thing where you've got cosine to the 5th power. So you bring an even power of cosine and you do a u substitution so that eventually you get 64/15. Cool. All right, let's keep going. I guess that's enough cylindrical stuff. We're all pros at that now. Here we get to talk about the spherical coordinate system. The spherical coordinate system is cool for things that are, well, obviously spherical in shape or have some kind of sphere-like shape to them. So spheres are really nice because spheres have a constant radius. And so they look just like a constant function in the spherical coordinate system. It's a constant function of the radius. These half planes are nice in the spherical coordinate system. I guess this would be the exact same in the, it would be pretty similar in the cylindrical coordinate system. I guess it would be a little bit easier to do in the spherical coordinate system because z values are taken care of by this new angle phi that we're going to talk about. And in the cylindrical coordinate system, you'd have to have an improper integral to describe an entire half plane because you need to go from z equals negative infinity to z positive infinity. So yeah, if you want to talk about an entire half plane, spherical coordinates, go to it. And then Cones are really nice in the spherical coordinate system because these are constant functions of phi, which is a new angle that we're about to talk about. So these kind of shapes are really handy in the spherical coordinate system. And, some objects are just easier to describe using two angles and a radius. All right, so this is a lot right now. I think we're going to come back to this stuff soon. I think I'd like to click on this GeoGebra thing and show you. All right. What we're doing. Okay, so obviously we are on the surface of a sphere here, and in order to not goober things up too much, I'm going to get rid of that, and I'm going to get rid of this parametric curve for a second, and I'm going to get rid of this radius for a second, and then there's this nice animation that we can do. Okay, in order to define a point on a sphere, what we're going to do is first, we have a radius. That radius is named rho in this scenario. So looks like a lowercase p, that's the letter rho. The second piece of identifying a point in the spherical coordinate system is an angle. This angle is going to be theta. It is, theta like we would normally think of it in the XY plane. So it's defined, as this angle coming off of the x-axis within the XY plane. So yeah, theta is just like what we saw in the cylindrical coordinate system. This new piece that we have is going to be an angle defined coming from the positive z-axis, so that you could kind of think of the domain of this new angle phi as it could be, as small as 0, and then you'd be on the positive z-axis. But when you get to pi halves, you're at the xy plane, pi halves. Something like that. And then when you get to fully pi, you'd be down at the negative z-axis. And so, yeah, this new angle phi, has a domain going from 0 to pi. Whereas, theta, like we normally understand it, has angles from, you could say 0 to 2 pi. I guess this is right now from negative pi to positive pi. But 0 to 2 pi should be fine for theta. Anyway, yeah, doing that would be fine. But phi is this new thing. But once you have a radius rho, an angle in the xy plane, and then an angle off of the positive z-axis, you actually have 3 pieces of information, and that is enough to isolate a point in space. And these coordinates are going to be really nice for some objects. What we need to look at now is, there's some conversion relationships between rho and phi and theta when you're trying to translate between the different coordinate systems, Cartesian, cylindrical, and spherical. I think what I'd like to do now is focus on the volume differential and why the volume differential is the way that it is. So, again, if we're cutting out a little piece of volume here, this bottom portion is a change in the radius emanating from the origin. So we're just going to call that one d rho. That's fine. which one was probably the next easiest? Let's do rho d phi. So, a little change to the angle emanating from the positive z-axis, put us along, a great circle on this sphere. And so, yeah, this length can be represented by rho d phi, very similar to the rd theta that we're used to in the xy plane. It's just the radius times a change in the angle measure. And then the final one, which is particularly confusing, is this rho sine phi d theta, which is really just r d theta, where r is just how far out you are in the xy plane. So let's go ahead and I'm going to put that segment here for r back in, and I'm going to create that parametric curve again so that you can see the circle. But yeah, once you start going up in the z direction, you get smaller circles than, a radius of rho. And we call the radius of this smaller circle r. And so, yeah, I guess this length can be represented as r times d theta, or change in theta. And yeah, r d theta turns into the sine of phi times rho because of this triangular relationship here. If we're using phi as our angle, and we're saying the sine of phi is the opposite r over the hypotenuse, which is rho, we end up getting the relationship that r is rho times the sine of phi. R is, rho times the sine of phi. So all together, we get the volume differential rho squared times sine phi times d rho d phi d theta. And if you have trouble remembering that, it goes really nicely with the tune of row, row, row your boat. Rho, rho, sine phi, d rho, d phi, d theta. That's the way you write a volume differential in the spherical coordinate system. Yeah. So that's what our volume differential looks like. And we're going to be able to take integrals of these kinds of things very easily because the functions will be simpler and the boundaries on our, top and bottom will be simpler. Okay, for example 4, we're not doing any integrals. We're just converting this to spherical coordinates. And we teleported. Okay, we're back. So one of the main things to remember is that rho is the radius of our sphere. And there's a relationship. I'm going to do this one in blue because that looks like the color that I've used. But x squared plus y squared plus z squared equals rho squared is a good equation describing a sphere of radius rho centered at the origin. So we're going to be able to use this to, create a rho squared after expanding x minus 2 squared out. We get x squared plus y squared plus z squared, which turns into rho squared. And then these 4s will cancel out because we've got a plus 4 there and a 4 over there. The final thing that we need to pay attention to is this minus 4x. Now x, remember that is r cosine theta from cylindrical coordinates, but r is rho sine phi. So, you know, I probably should have done this in a different color, but that's where the -4 rho sine phi cosine theta is coming, because R is rho sine phi according to that triangle relationship that we just looked at. And so, yeah, solving for solving for this, yeah. I guess one step that's kind of missing here is pulling out how, there I just drew it completely as a P. Pulling a row out from this left-hand side, I did it again. You would have rho, -4 rho sine phi cosine theta, because there's a common factor of rho there. So yeah, rho does not belong here. We pulled out this common factor of rho. So it's, rho -4 sine phi cosine theta equals 0. And again, we're in a situation where we're using the zero product property to, determine things. Either rho is equal to 0, or rho -4 sine phi cosine theta equals 0. And we would be able to say that from this portion, rho is equal to 4 sine phi cosine theta. Cool. All right, moving on. Example 5, and then I think there's an example 6, and then we're going to be done. Example number 5, we have to set up the general form for the integral of a function f of x, y, z over a solid defined as the first octant portion of this sphere. Cool. So that first octant portion is going to tell us some stuff about theta. If we're in the first octant, that means we're going to be in the first quadrant of the xy plane. So theta is going to go between 0 and pi halves. And then if, we're remaining in the first octant, the value of phi is going to start from 0 and go down to pi halves. So we've already got some, nice, measurements there for our angles on the outside. 0 to pi halves in both cases, for theta and for phi. And then, if we want to, come up with boundaries for rho, the radius, we use what we just did in example 4. And in example 4, we figured out that the radius was either needed to be 0 or, this outer radius of the sphere. And so those are the boundaries that go on the integral here. And then this whole mess is, in the situation that you were given something in terms of x, y, and z, you would want to convert those x, y, and z values into rhos and phis and thetas. And these are the ways to get that. I mean, when you're thinking about these spherical coordinates, I guess, you don't have to memorize that entire chart that I kind of just glossed over here. X is still equal to r cosine theta. But remember, in the spherical coordinate system, r is rho sine phi. And again, the y coordinate would be r sine theta, like we're used to seeing. But r is rho sine phi. And then this piece is, a little bit different. But the the z value is rho times the cosine of phi because it's this piece of the triangle, whereas r was rho sine phi. Yeah, z is going to be rho cosine phi. So yeah, and then we've got the rho sine phi d rho d phi d theta for the volume differential. So that's cool, right? All right, so we set up this integral. We're not going to solve anything because we don't have a function. But that's how you set it up. And notice how the boundaries here, you know, while being a little bit weird, especially, you know, this one being a little bit weird and new, most of them are constants. 5 out of the 6 boundaries are constants, which is really nice when you're doing integration. So yeah, that's the benefit. All right, last one, example 6. And yeah, we're gonna need to erase at least the starts here. I'm gonna try not to cheat there. Here we're just finding the volume of the solid. So all we have right now is this volume differential dv, and we're doing a triple integral. But yeah, in order to do this, the first variable that we're looking at is rho. And so rho is the radius. We're going to be looking for what's the smallest the radius gets, and then what's the largest that the radius gets. And since we're bounded above by a sphere of rho equals 1, we're going to be starting off at the origin as our inner radius, and then out to 1 as our outer radius. And so this will be 0 to 1 for rho. For phi, which is the one that comes down from the z-axis, we've been, you know, given information that we're bounded below by this cone, where we've got, yeah, pi6. So in the phi direction, we start off at phi equals 0, and we go until phi equals pi6. And that angle, since this is a cone, that angle stays the same all the way around. And since, you know, this is a cone and things are symmetric about the z-axis, when we look at theta, our angle in the xy plane, we're just going to go from 0 to 2 pi to get the entire circle of it. So this one wasn't too bad either. Then you would go through the motions of evaluating this integral with respect to rho first. Just, you know, undoing the power rule there. Sine of phi just acts like a constant. And then keep going, and eventually you get this wonderful fraction, which, you know, I never ended up you know, solving out for a specific decimal answer. But oh man. I mean, I guess that's fine. It looks a little bit suspicious because is this going to be a negative answer? And I guess that negative is introduced when we take the antiderivative of sine of phi. And yeah, antiderivative of sine is the negative cosine. Oh man, but why? So yeah, square root of 3 over 2 would be bigger than 1. And so this is a negative number in the end. Good grief, did I do the same kind of thing as I did at the end of, what video was that? It was the one with polar coordinates. Oh, all right, so on that bombshell, no, come on. It's not a negative volume. All right, you guys can totally figure this out. And if not, I'll be in class tomorrow and we can look at it together. All right. Or I guess it would be Monday. All right. See you guys. Have a good weekend. Bye.